Hi, this is David Greenberg. Welcome to episode 11 of Machine Learning at Helmholtz-Zentrum Gestacht. We have another really exciting, interesting, and I think very intuitively graspable paper today. It's similar to some previous work we've looked at, where we're using machine learning to learn the dynamics of a physical system. So we saw this in our very first episode with hidden fluid mechanics, where we had partial differential equations describing continuum mechanics, and without using any grid or anything like that, we had machine learning methods that just learned to directly, using the symbolic form of the PDEs as input, to learn to reproduce the dynamics. Then we came back to this at a later time point in this compressed pressure episode, where we had machine learning methods which learned to carry out the dynamic updates of pressure and velocity fields for fluids like smoke and liquid on a grid. And now we're coming back to it in another context where we have machine learning methods learning particle dynamics. So we have water, we have sand, we have this group we'll discuss as well, and we have a representation of these different materials as a lot of interacting particles, sometimes particles of different types, doing all kinds of interesting things. And with this different representation of the materials comes a different kind of technique where we're going to use these graph network-based simulators. So I think Marcel will mainly cover this paper. I will chime in with a few interested and sometimes naive questions. But the overall goal is to represent the dynamics of these materials. We start with a physics-based simulator, numerical simulator that already exists. We're going to run this, produce simulation data, and the neural network will then learn to run simulations by imitating this physical simulator, but we'll learn to do it in a way which is much quicker and easier to use. So that's my very brief overview. Marcel, I'll hand it over to you for a few more details.
Okay. So as David already explained, so this is going to be the main paper for this session, learning to simulate complex physics with graph networks. As David already introduced, so the graph networks are going to be one particularly cool feature that we will be just looking at very superficially this week. In the email that David sent around, there was a rather extensive review about graph neural networks as a research topic that's very big, that's very interesting, but it's one of these things that at least I always want to get a better idea of what's going on, but I never find the time to. So we'll stick mostly to these particular type of graph neural networks, which is graph networks or interaction networks. The terms might be a bit confusing, just keep in mind that the type of graph neural network that we will be talking about today is just one particular type. Okay, so much for the graph networks, or for the introduction of graph networks. So David already explained, so it's going to be about physical systems, just as in the sessions of, I think we called it compressed pressure a couple of weeks ago. We're mostly going to deal with physical systems that are behaving like fluids, but that are on a scale that's still very far away from actual climate systems. As we might care about them, it's essentially stuff moving in a box, as you can see here in figure 1. So these are renderings, so it looks continuous, and apparently for renderings you always need to add some funky reflections on the glass as well. But the systems that we actually are going to be looking at for this, these are discretized. So here in figure 2, you can see that actually the liquid, the water in this case, is composed of a lot of individual particles. So depending on the situation, on the simulation here, they train on the order of tens of thousands of these particles. They are generated, so there are physical simulators for this that give realistic rollouts, as they're called here, so where you can simulate the system for a given amount of time by updating the state according to physics. And the idea now is to, as we had a couple sessions ago, to take a sequence, like a video sequence, a sequence of frames, of snapshots of these physical systems as they evolve, and then learn a simulator based on machine learning that then learns how to update them into the future. There is a couple changes relative to the last session. The first one, the last time we talked about these kind of neural networks and machine learning techniques to learn how to update a physical system. And there's also a bunch of similarities. So the first similarity is that the overall structure of the model is somewhat similar as we've seen it before, in that the way that this is tackled by the authors is that you have this state at any point. So the superscript here is time, but we're looking now just as the state x, which is a concatenation of all the positions and velocities of the particles. And this gets fed into an encoder. Then there is something, which we're going to cover in a moment, that kind of forwards this in time, the state, in this case by a single update cycle of the numerical solver. And then from this updated state, there is a decoder. And the output of that decoder is then used to update the state, so the next frame. And in the context, all the context of this work, the output of the method is, where do we have it, is going to be directly related to the state change itself. So they're using an Euler integrator. This is a second order method where the output of the neural network is the accelerations of the particles. So just to quickly recap, what the type of algorithm that we're dealing with, what it does, it starts out with a list of all the current positions and velocities of all the particles, and it produces a list of accelerations for all of the particles that then are used in an Euler-like scheme. If I may quickly, wildly jump around, in an Euler-like scheme, forward Euler, to update the next state. So this is what comes out of the network, the accelerations, and then you, from the accelerations, from the forward Euler step, you get the velocities, and then with the velocities you can actually update the positions. And then the velocities and the positions then form the basis for the next update, so the state and the next update. So, how does this connect with the graph stuff? Well, you already see here that the encoder and decoder, they move between the representation of a long list of particles and a graph representation. So that's something that's very cool. We've encountered in the session that I've already cited quite a bunch of times, the session where we had the Wiewel et al. Paper. We've encountered a technique where it wasn't about particle-based systems, but they were actually discretizing the space, and they also had this update, this overall structure of an encoder, a processor, a decoder, but there the representation of the system, which here is a graph, it was just another vector. It was a sequence of essentially kind of arbitrary numbers, arbitrary in the sense that it's only meaningful to the algorithm. And it was a vector, it was fairly unstructured. And in this particular case, we have this fairly cool thing with a graph. And there's a particular background for this, where this works, where this is smart to do, not only cool, but smart to do in this case, because these systems, they consider of, well, these physical collection of particles, and the way they actually influence themselves is that whenever, for instance, if you just have one type, whenever they bump into each other, they exchange interactions, which can be phrased as sort of a message, passing from one particle to the other, and from the other particle back. And so
Marcel, can I ask a question just on behalf of anyone who may not have seen graphs too much then? What's the simplest definition of a graph we can give? I mean, it has edges and vertices.
Oh yeah, sorry. I might be covering this now and not only later. So a graph is a representation, as David just said, of vertices and edges. So you have a list of vertices. They are usually represented as these little shiny balls. And then you may or may not have edges between them. So if I quickly may switch papers. So this is one of the papers that we will be covering very shortly. That we had in the email as additional reading. So this is the one that actually introduces the kind of network that does the update step on the graph, the processor. And so a graph is a collection of two things. It is a list of vertices, and then it's a list of relations of edges. And the vertices might be either numbers or vectors, and the edges might also be numbers or vectors. And the structure of the graph is something very particular, because you can have edges and you can have no edges between two particular pairs of vertices. And having no edges is different from, for instance, having an edge with value 0. So a graph has a structure. The structure encapsulates relations between the vertices. In this case, you can think of these as being, in this case, it's actually quite explicitly defined as being close to each other. So in the system...
vertices are particles, right?
Sorry?
The vertices of the graph correspond to the particles of the physics simulation.
Oh, sorry, did I mix this up? So the vertices are the particles, and the edges, they are encoding closeness, like being close enough to actually matter to each other's trajectories. Sorry, did this somewhat cover the question regarding the graph?
Yeah, I think that clears it up, right? So you have the vertices, you have these particles in the physics simulation, each one is a vertex in a graph, and the edges of the graph are present or absent, saying whether these particles will interact.
Yep.
Right.
And the way they're constructing the graph is that at every point in time, they're having a little epsilon ball, if you like, around each particle with a free parameter epsilon that is actually explored on the paper. The bigger you set this value, the more neighbors you're going to get in the graph. And if you set this to be bigger than the box, then you're going to have a dense graph where every vertex is connected to every other, and then you have quadratically many interactions, which makes this thing very expensive. If you set it very small, then you might be missing out on relevant interactions that you need to capture for an update step from one time point to the next. So there's a bit of a free parameter of this method, but it has a physical interpretation, sort of, and in the sense that of the local interaction principle of physics. So this is how they construct the graph. Then the values, as I said, of both the vertices and the edges, they are vectors themselves. In this case, they are vectors of size 128, and they are actually learned embeddings. So what they do is they train. So for the graph consists of vertices and edges, and both the vertices and the edges are learned functions So epsilon E is for the edges and epsilon B is for the vertices. These are neural networks. So the one for the vertices, it takes the position and velocity of a given particle, and then it computes its embedding into the graph. And the same for the edges. So the edge of the graph is computed from a relation between two particles that is only defined for particles that are close enough within this epsilon ball. And for most of the setup in this paper, this is just the relative positioning. So you train two neural networks to create your graph. One that does the values of the vertices and one that does the values of the edges as a nonlinear function of the particles and the relative position. And that's how the graph gets set up. And then you have this processor, which is this interaction network. This takes a graph and it produces another graph through a sequence of message passing where messages are passed along from, onto each of the vertices, by each of the vertices, along all of its neighboring vertices via the edges in one message passing step. And then they do 10 so that they can have interactions of higher order. Again, 10 is... so Eduardo asks, the V's and E's are sort of hidden variables without clear interpretation, right? I mean, yes and no. There's this particular thing that, unlike in a, say, if you were running this just with a feed-forward neural network, every vertex corresponds to exactly one particle, and every edge to a pair of particles. Now, the vector that that is associated, like the embedding, this vector that is associated with the vertex of a given particle, it's a vector of a size, that the size is given by the number of hidden units that you put up in the output layer of this neural network. Like the ordering of those dimensions, and for the context of this paper, it's always 128. Those things are kind of without clear interpretation. So if you have a particle in 3 dimensions, you have 3 dimensions for the position, and then another 3 for the velocity, and then they, depending on another hyperparameter setting, they might append a bunch of recent accelerations from the last steps, but it's going to be a dimensionality of 3 to 15. And this V, which is the value of the vector that is associated with the vertex, is 128 dimensional, and that is, what this means is essentially only known to the network. Like, it's not interpretable from a human perspective. It's just a bunch of features that are extracted by the encoder network, such that the processor network has something that it can operate on, some rich nonlinear representation of what's happening in the vertex. In this particular case, there's actually there's this somewhere in the appendix, I think, there's a little remark that the encoder and the decoder network for the experiments of this paper could have been linear. So in that case, the V's would just be linear combinations of the positions and velocities. More generally, they can be arbitrary nonlinear functions, depending on how deep and complex you want to make these encoder and decoder networks. There's one thing that I wanted to say about these processes that might be confusing at first. So there is these processor steps that are iterated m many times. So there's m message passing steps. I just wanted to quickly remark one thing. One way to view a lot of graph neural network structures is as a generalization of convolution. Like, I think if you look at the, I haven't worked this out, so I might be making a fool of myself. If you look at the definition of the interaction network, and we can talk about this later if anybody has particular questions. Otherwise, I'm just going to skip over it. It has some operators internally. One is updating the edges, and the other one is then updating the vertices based on the updated edges and the old vertices. I think you can write convolution as very awkwardly through this. So this is a generalization of a single graph-to-graph operation through the processor is somewhat very reminiscent of a single layer in a neural network. And in this interpretation, having capital M many iterations of this is like having a deep neural network that does the update on the hidden state, this hidden graph embedding. And then that also explains, like they make this point of whether or not they tie the variables, the parameters of these hidden networks, whether they're all identical or not. That's then akin to having a 10-layer neural network where all of the weights are identical in each of the layers, or where you actually allow these weights in different layers to differ. Maybe that clarifies some of the confusion I had, at least in the beginning. So this is kind of the setup. You take a state, you make a graph out of it, and then you operate along the elements of the graph according to a principle of local interactions, where local both means local in the physical sense, because interactions happen along edges, and edges are only there if the particles are physically close, but also local in the sense of a single messaging pass is not, for instance, gonna relate this vertex, which is representing some particle, directly with this one. So there is a strong sense of structure of the problem that is baked into this update step. Again, very reminiscent of how a convolutional neural network breaks down an image-to-image translation by only comparing neighboring pixels. In some sense, well, not in some sense, but you can write a 2D lattice as you have for an image, where the pixels are on a 2D lattice. You can write this as a very regular graph, where just every node has 8 direct neighbors. And this is just a generalization, where you can have a different number of neighbors, and over time the neighbors can actually change. So the graph gets reconstructed at every time point from t to t+1. And that's the overall algorithm. I think that concludes my attempt of explanation. If anybody has more questions, feel free to chime in. Otherwise, I would be talking a bit more about the particular way that I find quite interesting that they're approaching how to use that. One thing I found really, really interesting is this whole idea of the network produces the output of an Euler integrator. So it's operating at the step length of the numerical integrator. So one thing you could do is you could uncouple that, right? So you could not just predict every single frame, but you could decide to update only every 10th frame or something. Anything that is fast enough for you to get fluid videos, where you might actually not need as many frames to get a fluid and nice visually appealing rendering video. I might actually at this point, if I quickly may, start some of these renderings on the background, just to show you what these simulations actually look like. So there is the decision, the explicit decision, to use these kind of networks to really learn one numerical integration step from the next one. And given that it's an Euler update for these simulations, like the data that the network is trained on, to be somewhat smooth, you will have to make these steps fairly small. As you can see, there's slow motion, so there's way more frames than you would need to get a visually appealing rollout, as they call it. So in this step, nice, by the end of the day of the video, you can actually see the discretization. This decision of making it a one-step update has an interesting, instead of directly producing the video, it has an interesting related question, and that is about predictability. And that is something that in climate and weather we might be carrying actually a lot. It's not phrased that way, it's phrased as rollout. So a rollout is you start with a state at t0 and then you do a bunch of temporal one-step updates, k-many, and then you get this sequence of states. So every x is by itself a list of individual particles and their velocities and their positions, and then you have them at different time points. And then what the model does, it starts with the exact same initial state, so there's no wiggle, it's the same x, and then it produces a bunch of predictions based on its own output. So it predicts a first state, t1, from the initial state, and then it feeds its own output back into itself. So it's if you simulate from the model, it's really taking over the simulation fully. In this particular case, unlike a couple of weeks ago, where some of the dynamics were actually still handled by essentially physics, code that does the physics, and that immediately backs the question: like, how well does this work if you just let it run? Like, are errors going to accumulate? Does it even work? Is it feasible for these kind of systems? And there's a bunch of interesting stuff that I will be talking about now in the more method section. And it's really related to this rollout number, k. So you can see, so n is the number of particles. As I said in the beginning, this can get on the order of tens of thousands. And this is possible because they have this structure where they essentially use this kind of convolution-like structure in the particles that you don't need to map the entire 19,000 times number of actual dimensions per data point into a state of the same dimensionality in the next time step, just as one gigantic monolithic prediction problem. But you can break it down to, well, what you need to get is you need each of these 19,000 vertices, right, and then all of the edges. So you're breaking it down into a lot of smaller problems that are very natural to solve because there's underlying physics that are having the right structure. So you have the right inductive biases, as you say. But getting back to this number k, this is the number of rollout steps. You see that it's in the hundreds and in the thousands. So that's like taking a function to the 2000th power of itself, and then hoping that after you've done that, the errors haven't so terribly accumulated that what you get doesn't even resemble your system anymore. What you could get is, in principle, what you could get is, if you're not careful, that all of your particles leave the simulation box. So there's a bunch of things to notice, and a bunch of things that are really cool that they haven't seen yet, that they're actually making sure to have a good look at in order to make this work. So you see a one-step error that's on the order of 10 to the minus 9. Across most of these systems, there's a 10 to the minus 8 here. And then you have a rollout error, which is if you take the system, if you take the emulator that you've built from the machine learning and you iterate it up to 2,000 times on its own output, like on what order is the rollout error. And you're losing several magnitudes, orders of magnitudes in the mean squared error, in this case, of the system state after the rollout. But notice it's still small. So every variable here is z-scored, so the typical error is on the order of 1. The typical size of the stuff that you want to predict, and then you take the mean squared or error over, is on the order of 1. So 10 to the minus 3 is still okayish. Importantly, it's small. It's smaller than the state. it's not growing unboundedly. And there's one thing that they talk about that they really had to do in order to get that running, and that is training noise. So maybe one more attempt. I'm not sure if this got across why I'm so excited about this. Imagine you're having a linear system where the next state is some matrix. I don't know if anybody can see. What do I have? Quickly gonna help myself with a very low tech solution.
Can I climb in with a quick question, Marcel? I'm not quite getting the size of the errors to evaluate how big the numbers are. How big are the boxes that they're simulating in? I'm looking for that, but I'm not finding it.
That's on the order of 1. So they z-score, we normalize all input and target vectors, element-wise. So that means that they're also normalizing the positions, element-wise. And they're having the error, the mean squared error on the positions, where did I write this? Per particle. No. Well, we're not going to find it right now. We use particle-wise mean squared error. So if particle position is z-scored, then the boxes should be on order of 1, right? Or am I getting this wrong?
Right, that makes sense. So then these are quite small errors. I mean, 10 to the minus 9th is basically the precision of floating point.
Yeah, this is one step. You would hope that it doesn't shoot particles all the way across the box in one step. So these should be small. The interesting thing is rollout error. The point I just wanted to make, and maybe it's very stupid, stop me if it is. I just wanted to say if you have a new state and you have this as a linear function of the old state, and then you want to do this for, I don't know, can people see this?
Yeah, we see.
Then essentially you have a to the power of n times x. If you want to do this for let's use capital K. If you want to do this for k many steps, and now if the matrix A has some eigenvalue that is very close to 1, and you're making an error and you're making that eigenvalue slightly larger than 1, then a to the power of k has this eigenvalue that is slightly larger than 1 to the power of k. If k is 2000, you might end up with a very large number that you're multiplying now with a very large number for an eigenvalue that you're multiplying now with your input. So long story short, you may shoot out the state like completely into absolute nonsense. And this is for linear system, and for most nonlinear systems, you might get even worse effects than that. Sorry if that wasn't clear. So it's fairly cool that they have a good handle on rollout errors, and that they manage a way to keep it from kind of having this nasty feature of it might explode. It might become completely unreasonable if you let the artificial system run for a long time. It might become numerically unstable. There's this cool trick that they use that I'm not 100% sure if I understand it intuitively how it really works, but here's the idea. What they do is they add noise to the inputs during training, and the rationale is that if you do a rollout, like you take the output of the network, which is a prediction for the next state, and you feed that back into the network, you want the network to become slightly robust to small errors in its input and still predict the output. And the training output is well within the box, so that's nicely behaved states. So if you slightly corrupt the inputs to the network and you still robustly predict the next state from it, then apparently this really helps stabilizing training by this idea that it becomes robust to slight nonsense in its inputs. And if you remember that you're never going to perfectly predict the next state, and you're going to feed its own outputs to itself, being slightly robust to slight nonsense in your inputs apparently really, really helps. That's a very nice trick. That they also say it is one of the big factors that makes this not work. But I've talked a long time about the method and some of the cool things. I haven't really shown too many of the results. So this is a 2D setup, as I guess you can see from the figure. So you have different materials and starting conditions. So this is the X at T0 and the top row, and then you have a bunch of different scenarios from the first to the last column in increasing complexity generally. So the first 3 columns are just learning different dynamics. So you have different materials that have different properties. The simulator, so the data that the network is trained on, knows these different properties. So the dynamics of the physics of the training data are different, and then you hope that the network picks this up. So if you compare the first with the very last, so this is what you get from the physical simulator. It takes the initial state, it integrates it for a bunch of steps. So this isn't just one step. This is, I think, the beginning and the end of a rollout up to a certain point. You see that in this slightly, I always think it's slightly funny way of doing initial states is they take these different viscous and fluid materials, they give them initial shapes that will then influence just how the rollout plays out under gravity, and then what happens is these things just drop and then behave like fluids, as you would intuitively expect them to. And now you have this training data, not just the first to the end of the rollout, but you have, of course, all of the steps in between. You train this network, and then afterwards you do a rollout through the network. So the initial 2 predictions, so the first to the second column, now it's just this network iterated a bunch of times on its own output. And then once you've iterated at just as many rollout points as for this trajectory you've done it with the simulator, the physical one, you compare the solution. As you can see, it's beautifully matching up. So the first 3 ones are just different materials. Goop, my personal favorite, is a somewhat viscous material, and you have water, and then you have sand. The thing that makes these look differently is, of course, the different properties of the materials, friction, and viscosity, viscosity. Then they step this one up. That's fairly cool. They introduce a bunch of special particles that may interact with the particles that you're actively trying to simulate over time, but they themselves aren't affected by. They're unmoved, so this is what makes them rigid objects. So you get these interesting interactions, not just among the particles of the material itself, but also with objects. You can see you can build these barriers and ramps. One thing that is very interesting is you can actually learn the interactions between different materials at once. And there's a little trick that is very easy to point out, at least the relevant part in the text. If I can find it. This is this. So this is the state for a single particle I at a single time point tk. It is the position, it is the current velocity, and then it's the past velocities. So I think before I said it's also the accelerations, but it's actually only the velocities. And then there's this extra thing, feature functions, F for feature, I guess, that is just appended to every single vertex, and that corresponds to a single particle. And this one, for instance, can give the actual material that this particular particle consists of. And since these kind of states go into the input of the processor, it can take, when it's actually computing and updating the interactions, it can take this into account. So you can get how different materials not only interact with other particles of their own material, but also of others, which is pretty cool.
So I think you have a kind of a gray window on the left side of your screen, partly blocking your screen share.
Is this getting better?
It just moved. It just moved a bit.
Can I close this?
Maybe if you share your monitor instead of your... Yeah, there it's gone. Great.
Okay, sorry for this. It was just my chat box leaking in a bit. And then there's there's other cool stuff that it generalizes very well to stuff that it hasn't seen in the training. And this shows you the idea behind this is, so in this particular case, they create, and from the description I take it's here, they create a constant water influx. So they create a bunch of particles that they add at a particular point in the 2D box, such that after a certain time, there's more particles in it than it started out with. And this kind of situations they didn't have in the training. The idea is that if the network actually captures what's going on in the physics, in the sense that it really describes, first of how do particles move, like they tend to keep their velocities unless they're interacting with stuff, and when they're interacting with stuff, it depends on the position, the velocity, and the kind of the other particles around it. If it's actually learned this physics, then these basic principles of physics, then it should actually very nicely generate to situations it's never encountered before, like changing number of particles, a constant influx of particles in this case, and still give you reasonable results. And as you can see, if you do a certain rollout over a certain length, there's now slightly visually bigger differences between the states. But it's also getting a much harder problem of this chaotically behaving fluid. And then there's other stuff. For G, to be honest, I just wouldn't know what else they changed relative to the previous column, other than they just added a bunch. That they showed that this still works with multiple materials. There might have been another change. Sorry if I'm overlooking this. But then H is that it also nicely generalizes to completely new domains. Like you change the box, you change the barriers. You give it different numbers of influx with the number of particles. When new particles come in, funky shapes, the hippo here. And it still works if it has learned the right interaction of these particles. Meaning that if you throw more and more at it, the graph may grow, but the way that the graph has to be updated, if it's correct, if it's based on physical principles, it should generalize nicely. So that's the main part regarding the results. Then there's another cool thing.
There's a few questions from the chat, I think.
Yeah, I just closed my chat window. Sorry, I can't see them. Can you read them?
Yeah, I'll read out. We got one from Felix Stila. Could the ability to generalize be related to the fact that they learn embedding? So that, for example, they don't just operate directly on the original physics representation of velocities, positions, materials types, but they learn these abstract representations. Could that help them generalize?
That's a good one. I don't absolutely know, I have to admit. Generally, these nonlinear abstract representations would make me more afraid that it doesn't generalize, because it might be something that it's doing particularly to the actual training data that it's seeing to fit that very nicely, so essentially to overfit. Usually the simpler you have stuff, the easier it is. If it is necessary to non-linearly represent the nodes to implement the physics, then it's just necessary. I'm not sure if this would make it generalize better, it would just make it work. I think what makes it generalize so well is that the algorithm, the structure of the algorithm through the embedding in the graph just so very well captures the physics and the structure of it. In particular, this local interaction principle. And there's something that I discussed with David that I'm not entirely sure. I would need to look up the details of, well, first of all, the equation physics, the physics of the equations that are implemented here, but also probably how the particular simulator actually implements them. It might be that you can write the numerical simulator in this framework if you choose the right types of networks. Like you might actually have a graph representation of the particle physics. And if you didn't have the simulator as a monolithic block of, I don't know, Fortran code or whatever, you might actually rewrite the simulator itself such that it produces the same output up to machine precision in this thing. The reason I'm coming up with this particular, sorry, it might sound a bit weird, but if you remember the Lorentz 96 problem from a couple of weeks ago, we actually rewrote the update equation, like the analytical update equation that defines the Lorentz 96. You can rewrite that in neural network form, and then you can write a machine learning algorithm that perfectly solves this by just choosing the weights of the neural network analytically. And I wouldn't be surprised if this particular structure would be so general that you could actually perfectly represent up to machine precision what the simulator does. And then the task of the network is just to learn it, and then making it as simple as possible without a nonlinear, with as simple of a nonlinear embedding as possible, would then probably guarantee that it generalizes. There was probably a lot more rumbling than what was necessary.
Go ahead.
Sorry, did that answer the question?
Yeah, I think that was exact. I would completely agree with that answer. I would maybe Felix, if you want to chime in, if you have your own, you can David answer. I would just add an additional layer of intuition, because I think that exactly what you said, Marcel, about local structure and the structure of the graph, and the architecture of the machine learning technique we're using matches the problem. But just to give it intuition, if you imagine all these different scenarios where you have a ramp over here, you have sand on the left, you have poop on the top, you have water flowing left and right, there's a huge diversity of scenarios, and it's very difficult in machine learning to deal with a scenario you haven't seen. But what's going into these machine learning techniques isn't the whole scenario. It doesn't operate on the whole simulation at once. It operates in these tiny little neighborhoods where you have a little bit of water, a few particles of water, maybe a boundary ramp, maybe a bit of sand. So all these tiny little neighborhoods are where the action really happens. And if it can get the right answer in these tiny neighborhoods, it'll get the right answer everywhere by kind of repeated iteration of the process. So even if the full simulation has a new structure we haven't seen before, the local neighborhood patches are going to be familiar, and therefore it's going to work. This is my intuition of why this should generalize. There's some more, so I don't know, Felix, if you want to chime in with follow-ups or if that answered your question. There's a couple more questions in the chat. Eduardo's asking, there may be situations in which the kind of material a particle belongs to depends on the density of particles, e.g. in phase transition, liquid, gas. And I know that in some of these simulators, particle simulators, they do use basically the local density of particles to compute pressure in this kind of a kernel density approach. But yeah, you could have changes from phases of matter. Do you have anything on this, Marcel? How this fits into this framework?
So this goes a bit back to this representation of the type of particle. So this is the information of the particle, and then there is a vertex that is a nonlinear function of this, if I find it again. So we were talking about x, about this x, and then there's this vertex, which is the nonlinear representation of it, which doesn't know yet about neighboring particles and pressure. Okay, but if we then go into the paper, and now notation changes, I'm kind of sorry about this. So this updates a edge based on a pair of vertices and the old edge. There's different. This is more general, but R and E kind of play the same role. O is what used to be our vertices, and you can then update the vertex based on the old vertex, and well, we think there should be a sum, the sum of all possible neighbors along the edges. So long story short, I think through this function, in principle, you can update the state, like the material type, at least in the hidden representation, based on how many particles are around it. So I guess it would be possible for the algorithm to pick this up and give dynamically changing material types through the step of applying the processor n times. But it doesn't really override x at this point, so we'll have to do that in the next step, because it only updates the velocities. It doesn't hard update the material type, but I think you could change that. So I guess, it would be possible by the architecture. How to generate the training data, then I don't know, but I guess it's possible.
So one issue I'd see there, I mean, looking at these particles and the different types interacting, one of the first things I thought would be so cool to have chemistry happening as well. But whether you're talking about, changing from liquid to solid to gas or chemical reactions, there is a potential problem I see, which is that these changes are discrete. They're an all or none. Either the reaction happens, the phase transition, or the chemical reaction, or it doesn't, which means it may not be differentiable anymore. These networks are trained by having all their operations be differentiable with respect to their inputs as well as the neural network weights. So if you have these phase transitions, which if they can vary continuously along some axis, right? So maybe the particle starts behaving more ice-like, then more water-like, then more steam-like, then maybe it works. But if you have a hard switch, I think it may be difficult to train these models.
Yes. I'm also not going to find that right away, but I think they have they actually embed the type of particle is embedded in a 16-dimensional vector, and I would have to look it up if that thing actually necessarily has to be binary, or if you can make this continuous, and then you could differentiate through that.
One more question from the chat. Johannes asks, is it possible to check momentum and energy conservation?
That's a good one. I don't know. I honestly don't know right now. I think there was something about in the other paper, but not in this one. So in the methods paper, they were talking about this briefly, at least about it being important. But no, I'm not aware of, and I'm hoping I'm not talking nonsense here, but I'm not aware of them ensuring that.
In principle, it should be pretty straightforward, right? Both to check whether
checking,
globally and locally conserved.
Checking, they could and they don't. I mean, for them, it's probably if they're, I don't know. I mean, it's already quite a success that you don't lose particles from the box, I think.
I just want ask that question because maybe it's related to the question in general, what kind of metrics you use to quantify the quality or assess the quality of the simulation, isn't it? So you can do it in terms of RMS differences in positions or velocities, but you could also look at the quantities that should be conserved somehow.
Yep.
I think basically what happens in this system is that you translate or transfer potential energy into heat, basically, isn't it? That's what's happening. That of course that transition should be also follow the conservation of energy and momentum.
Yeah, I think you're very right. They do not evaluate the evolution of, say, the quality of their rollouts with much more than the error. They have a little part in the appendix where they try out different errors, but it is essentially, it's the type where you compare, here it is, so they have mean squared error, then they have optimal transport and NID. So very quickly, so mean squared error means you directly compare the position of each particle, but as they say, like what could happen is that two particles swap positions, then the state of the system kind of looks the same, because particle identity doesn't matter for the state of the system. Optimal transport is a measure that's more on the distribution of particles, so it kind of compares to system states without particle identity mattering. So they have different losses, and they have essentially what you're describing or what you say would be very nice. They don't have that. They only have that through mean squared or some sort of error between their system rollout and ground truth. So if they had no error, then these quantities would necessarily be conserved. But given that they do have error, it would be very interesting to not just look at rollout mean squared error state-wise, but at higher level.
But I could imagine that this also depends very much on the kind of application that you're talking about, isn't it? So for some applications, it may be quite critical to have all these quantities conserved, or maybe also get maybe extreme values, right? Extreme velocities and things like that.
Yep.
But for most applications, probably these RMS metrics make sense.
I think they have this one case of a failure case, which would be something that is relevant here, which is not, I don't know, where they looked at some stuff that doesn't make any sense in this particular case. So they're not looking at energy conservation, but they're looking at aphysical behavior. Like this one, I mean, the group in particular does stick to stuff, but probably this should have fallen, at least according to my internal physics. Generally, it's very tricky. This is one of the things that might be very tricky for this particular approach, where you do a single step update, is during training, it's very hard to punish the model for deviating from these kind of global properties on a longer scale. So one thing I could imagine is, as you said, either you have a bunch of things that you really care about, like energy conservation, and then you add an error term. But if you, to the loss, and just say, like, look, neural network or machine learning algorithm, I want your output to not only be close to the next one in mean squared error sense, but I want to have I want to really make sure that it's the energy balance or the different components of the energy, potential and what are my words? Temperature, that these be respected. Like you could compute the potential energy across all of the particles in the next step predicted by the network and the next step actually coming out of the simulator. You could add a mean squared error term, and then you could say, like, look, I want you to predict every single particle position, but in particular, I also want you to have an eye on this particular function of the entire state. Yeah. And you could do this with a bunch of other stuff that you care about. The problem is, if you do this on a single step, it might not really behave so nicely if you do a rollout. It might still diverge. It's not guaranteed. If you did a rollout as part of the error, and they discussed this, I think, if I find it again. So this is a rollout error, and this is the one-step error, and they actually talk quite verbose about why they go with the one-step error. But one thing why the rollout error is kind of nasty is if you have a neural network or an operation or any kind of machine learning algorithm that predicts one step, and then you apply its own output to its as its own input multiple times, then the gradient you have to take through all of the iterations of the function of itself. So making sure more long-term that, for instance, energy is conserved by adding a rollout error, which I think would probably do it, is technically very challenging. So there might be cases where you actually hard encode it in the graph, like you have another strong inductive bias. So for machine learning algorithms, there is, if you want to build some problem-specific stuff into your algorithm, you usually call this an inductive bias. And then there's hard and then there's soft constraints on this. Some of them can be in the architecture, the hard ones, and some of them can be in the loss. Adding another loss time would be a soft one. You could maybe also come up, I mean, not me, but someone could come up with some graph network that has global properties like energy that are consistent. Potentially, I don't know, just an idea. I know that there has been some work with convolutional neural networks that they preserve some quantities when they're trained on data from climate systems, that they try to preserve quantities locally to very high machine precision fidelity. I'm not sure if there's similar stuff on the graph, but as I said, graphs and convolutions are kind of related. Sorry for me rumbling again.
I have one more kind of comment or question about something you said earlier, Marcel, which was the idea of how impressive these rollouts are, that they're going for very long timescales of prediction and they're getting the right answer. And what's even so impressive is they're insisting not only do you have water in the right place, but it has to be the same water particle as in the original simulation. But maybe it's because, unlike, say, the L96, which we covered a few sessions back, these simulations tend to have equilibrium states, right? You let them run for a while and they kind of end up in some fixed position. They don't go on chaotically forever. So maybe the systems are just inherently more predictable.
I think you see it very beautifully in the second column of the figure C3. So this is mean squared error, optimal transport, and MMD. What was it called again? Help me, David. Median.
Maximum mean discrepancy?
Maximum mean discrepancy. Thank you, sorry. So, sand, it tends to start and then in a certain configuration, and the rollout error at the beginning is small and under all losses. And then it tends to settle into, a heap of sand at the bottom, right? And if you use a loss that really tracks individual particles, then actually this is really hard to predict. You see the mean squared errors, they go up and they stay high. For optimal transport, exactly the thing that you say, they might be easy to predict. If you don't care about particle identity, you just want to say, like, where is the heap of sand at the end of the simulation, you can actually see this, that the system in some sense is extremely easy. Like, it has really messed up individual particle positions, as you can see at the top row, but the distribution of particles spatially within the box is kind of easy. It's trivial. It's at the bottom. Is that what you were going for?
Well, I mean, yes, there's that aspect of it, right? But I also just mean that the systems have a stable point. You know, they don't kind of splash around or roll around forever. They come to rest. The dynamics are stable, as opposed to L96, where the dynamics are chaotic. So whichever measure you use to compare them, like, you know, small perturbations will lead to large errors in the future. Just maybe this is an easier problem.
It's a different kind of problem in the sense that, I mean, first off, again, I would still say it's not so, I mean, at least in the mean squared error sense, if you care about particle, exact particle position, just predictability seems to have a certain limit. Like, it flattens out. I guess these are just then the kind of errors that you get. You see, it doesn't increase forever. And the other thing to this is, and that's in the nature of the setups, and it has to do with these funky initial states starting in very fragile states that aren't particularly stable. This whole thing is like I don't know, like it's meant for finite rollouts. It's not like a climate simulation, which is meant to run very stably for a very long time. It's much more, I guess, in this sense, and sorry, please don't crucify me, it's much more like weather, and that you have a very specific initial state and you want to know how the rollout is up to a very specific horizon. And the exact dynamics on the way matter because you really care about the exact state, in a sense. Whereas for the L96, at least in my head, I always run it for very long, and I don't exactly necessarily care for the exact state, other than in these kind of graphs where I want to see like how long can I actually exactly predict it. This is just maybe just me.
Well, cool. Do we have any more questions on group chat? Anyone want to chime in, or do we have any more questions on YouTube 2 minutes ago? I don't think so. Well, I guess we can basically wrap up. Anything anyone want to add? Anything you want to add, Marcel?
No, other than that, part of our slight technical problems in the beginning were that David and I tried to add at least a limited physical component to our meetings, and then spontaneously we decided. So next session, we are trying to set this up that we can have some people meet physically at the Helmholtz Center Gestacht in a seminar room, which is not particularly relevant for everybody in the YouTube stream, I realize, but for those people here in the chat, it might be interesting, at least some of you.
Yeah, so we'll try to send you an update. We're going to choose a seminar room and try to meet there in 2 weeks, obviously with a limited number of people and observing the appropriate social distancing rules. Yeah. So thanks to everyone who tuned in. Good questions, really cool paper. If you haven't already, go check out all the videos on the website. They're really beautiful. It's really nice work. And they have promised to release code at some point, so we will keep our eyes open for that. Thanks, everyone.